Okay, let's dive into this. Today, we're stepping away from the messy, everyday world of friction and heat, and we're entering a space of pure, frictionless geometry. We're going to explore one of the most elegant and profoundly beautiful phenomena in all of physics. As we'll see, we aren't just looking at superconductivity as some strange quirk of materials, but as a deeply atmospheric, highly organized collective state. You know, electricity normally pays a toll. When you think about ordinary current, imagine electrons trying to move through a crystalline atomic structure. They don't move cleanly. They repeatedly scatter from atoms, they hit defects, and they bounce off vibrations. Every single time they scatter, they kink, they lose energy, and tiny pulses of heat are generated. That chaotic loss of energy, that heat, that is what we call resistance.
But inside a superconductor, that toll entirely vanishes. The chaotic, dissipative scattering of ordinary current we just talked about, it completely gives way to smooth, continuous wave paths. The noise just fades. The traces stop colliding and begin to flow perfectly. And this brings us to a truly profound definition. Superconductivity is electricity moving without ordinary friction.
Now, we're not just saying electrical resistance gets very low here. It drops to absolute zero. A current can continue to flow infinitely without the usual loss of energy. This isn't just very good conductivity. It is an entirely different state of matter. Furthermore, these materials completely expel magnetic fields from their interior. And because of these massive, macroscopic effects, we arrive at a startling truth. In a superconductor, quantum mechanics becomes visible on the human scale.
So how exactly does matter achieve this impossible state? Well, it's all about descending into order. Superconductivity only appears below a very specific threshold. You see, at ordinary temperatures, the atomic lattice is simply too noisy. Atomic vibrations constantly disrupt the flow. Electrons behave like separate travelers, aggressively pushing their way through a crowded city. But as the temperature drops below a critical point, the internal disturbances fall. The material becomes quiet enough for an entirely new collective state to form.
As those atomic vibrations settle into a calm, ordered phase field, a new reality emerges. Simply put, cooling lowers the cost of coherence. In this incredibly quiet environment, electrons no longer have to act as isolated, random actors. The sheer lack of thermal noise means the energy required to align, synchronize, and move together drastically.
Once that cost drops, something genuinely remarkable happens. In conventional superconductors, electrons form what we call Cooper pairs. Now, we normally think of electrons as strictly repelling each other, right? But here, they become linked through a gentle distortion of the material's lattice itself. They form a paired wave structure that moves as one. And this pairing is exactly what allows many electrons to enter a single, shared quantum state.
And this brilliantly illustrates something absolutely crucial. We really have to stop thinking of these particles as discrete little billiard balls. A Cooper pair is not just two electrons. It is a small agreement inside the lattice. It's a localized partnership, mediated by the very environment that used to cause them friction, which now allows them to navigate the material in perfect harmony.
To truly grasp this, let's view it through the lens of general emergence mechanics, or GEM. Now, GEM doesn't replace the standard physics of superconductivity. Rather, it gives it a visual logic. In this framework, resistance is simply a sign of local friction in the coherence geometry. Scattering creates gradient noise. Heat is just the cost of failed smooth motion. GEM shifts our perspective completely, so we see the current not as cartoon electricity, but as collective geometry.
When millions of these Cooper pairs phase lock into one smooth wave spanning the entire material, the lattice becomes a single coherent field with absolutely no jagged phase breaks. The material finds a global, low-curvature collective state. Quite literally, a superconductor is matter discovering a frictionless route through itself.
Let's actually visualize that route. Imagine one path that's jagged, kinked, and dissipative. This is your ordinary current being repeatedly interrupted. It scatters, it heats up, and it loses coherence. But then imagine a second path that is smooth, continuous, and pristine. This is the low-curvature channel of a superconducting current. It moves through a pre-negotiated channel where the collective state protects the flow from ordinary scattering.
It is vital to realize that the resistance disappears simply because the motion no longer has to renegotiate the atomic lattice at every single step. The path is already clear for it. As the GEM framework concisely puts it, zero resistance is not magic. It is geometry without drag.
Now, this frictionless geometry doesn't just affect electricity. It extends to how the material interacts with the outside world. And that brings us to the macroscopic magic of the Meissner effect.
When a material enters a superconducting state, it literally reorganizes magnetic geometry. Magnetic field lines are actively expelled from its interior. This isn't just some parlor trick, it's the absolute refusal of the coherent state to admit incompatible field patterns into its pristine internal environment.
It is incredible to think about magnetic field lines approaching the superconductor, but then gracefully curving away. The material forms a perfectly clean, geometric exclusion zone. It is a stunning physical truth. The Meissner effect is geometry made visible.
So the crucial point is how this exclusion manifests in physical space. When you see a magnet floating above a superconductor, it's so easy to think of it as anti-gravity. Actually, scratch that. It's not anti-gravity at all. The magnet levitates because the system finds a highly constrained, stable boundary relation between the magnet, the magnetic field, and the superconductor surface currents. They lock into a stable configuration. Levitation is the shape of exclusion.
And this perfectly organized flow has profound, real-world applications. This frictionless geometry is what powers the massive MRI magnets in hospitals. It supports the incredibly delicate architecture of quantum circuits. It enables precision instrumentation, and it points the way toward future energy grids capable of transmitting power across entire continents without losing a single watt to heat.
But beyond the technology, there is a deeply profound philosophical implication here. We're so used to a world where everything decays, where everything eventually grinds to a halt. But superconductivity teaches us a deeper, stranger lesson. Friction is not always inevitable. Under the right conditions, matter can successfully negotiate a route around it.
And this builds into an even grander perspective. In general emergence mechanics, superconductivity is not just an isolated miracle. It is one of the clearest examples of a scale-free principle in nature. Systems persist when they find admissible geometries that reduce destructive friction. A molecule bonds when wave geometry lowers total cost. A cell lives when gradients can be maintained. A mind persists when patterns can recover. And a superconductor conducts when the whole material locks into a shared, low-friction state. Superconductivity is frictionless geometry made visible. It is matter entering a wholly different admissible state. Below that critical temperature, the noise falls, the Cooper pairs form, the phase locks, resistance completely disappears, and magnetic geometry is expelled. Electricity flows without resistance. A magnet floats gracefully above a surface. The material does not fight friction. It finds a geometry where friction cannot enter. For one rare, beautiful moment, quantum coherence becomes something we can literally see.
So think about that levitating magnet for a second, suspended in perfect geometric harmony. And ask yourself, is superconductivity just a strange material property, or a glimpse of what matter can do when geometry defeats friction?